the second derivative test for fxy. If you're given a two-variable function, what is the second derivative test for it? Now, let's do a slight review about the calculus 1 for calculus for a single variable. If you had f prime of a as 0, so that it's a critical number, and if you had f double prime of a as positive, that meant at x equal to a, f has a relative what? Maximum, minimum, what? Minimum, yes. Now, the way I remember this is by writing down the following. It's if the second derivative is positive, it's a smiley face. So second derivative positive means it's concave up like that. And therefore, at this point where it has a flat horizontal slope, it's actually a relative minimum. And for the case where f double prime of a is negative, it has a maximum because if the second derivative is negative, it's a frowning face. So at the point where you have the horizontal tangent line, it's the relative maximum. Okay? So that's how I remember things in calculus. And I want to come up with the criteria very similar to this one. It's just more complicated because now we have to think about this additional case where we have the saddle point. Okay? But before I move on to give you derive this formula for the second derivative test, I need to talk about one particular property of partial derivatives for two-variable functions. If a function has continuous second derivatives, then there's a theorem that says the two derivatives commute. So if you take a function and differentiate by x first, and then differentiate by y, that's same as taking a function and differentiating by y first, and then differentiating by x. They're the same. Now, I don't want to prove this. Let's just think about an example. Let's say f of x comma y is x squared plus 3xy. Okay, if you differentiate by, if you do a derivative by x, what would you get? 2x plus 3y. 2x plus 3y. Then if you differentiate this by y, what would you get? 3. If you do a partial derivative with respect to y, you get 3. Now let's first differentiate this time by y. What do you get?
X squared plus 3.
No, x squared differentiates to
0.
0 because you're doing partial derivative, so you get 3x. And then you differentiate by x, what do you get? 3. By the way, this instead of this, sometimes people just write down round x. That's what I'm writing. If you differentiate by x first, and then y, you get 3. If you differentiate by y first, and then x, you get the same thing. It's still 3. And then, you know, in calculus 3, in multivariable calculus, people use all kinds of notation for the same thing because it's convenient to have many different ones. It's complicated, so depending on the situation, it's better if you can use this symbolism more than the other one. So sometimes you write partial derivative with respect to x as this, sometimes like this, and the one that I'm going to use mainly today will be f differentiated by x. So if you do a subscript with respect to x, that's another way to write down the partial derivative. Okay, the 3 ways. this. Okay, so now we're ready to derive the formula for this second derivative test for two variable functions. Now what we want to do is the following. Let's say you have a function whose graph is shaped like a mountain. And let's say f a comma b is the relative max. Okay. Now, in that case, what is f x? Would that be positive, negative, or 0? What do you think?
0.
No, fx will be, if you differentiate once, it will be 0. Right? But if you differentiate twice, what kind of geometrical content does this have? It tells us the concavity, right? The second derivative would be what? Positive or negative? It would be negative. It's this case, right? It's like this. It's a frowning face. Okay? So partial with respect to x is like you're chopping up this graph and looking at the cross section when you're cutting it by zx plane. Okay? So if you cut it by a parallel plane to the zx, passing through this point, and you try to just climb up and go down this mountain, right? As you're going, and you're looking for the second derivative, that's like looking at the concavity of this, and because it's a frowning face, it must the second derivative must be negative. Okay? That's what we know. Okay? So this must be negative. Now the unfortunate thing is, this alone is not enough to guarantee that it's a relative max. You might say, oh, okay. Another thing that you should also, it should be clear is that fyy must be negative too, right? Because you can do the same thing for the y direction. It's still the frowning face in that y direction. And you might think, well, fxx negative and fyy being negative, that's good enough to say that it's a mountain-shaped thing, so it's a relative maximum. Unfortunately, that's not true. Okay? We will end up having something more complicated. Okay, so let's try to work on it. So here's how we do it. First, we pick an arbitrary vector u, a comma b, in some arbitrary direction. I could have noted this as cosine theta comma sine theta, but that will make it too crazy, so we don't want to do that. It's just a comma b, where a squared plus b squared is equal to 1, so that it's a unit vector. But we're not going to use that back. We'll just say that. And then I'm going to do this. Because I want to know the concavity in that direction, I want to take s and differentiate by u, and then take that and differentiate by the directional derivative with respect to u twice. Okay? So that will be like, if you're passing through this highest point in that direction, I don't know what direction u is, but let's say you're passing through that in some crazy direction, and I want to make sure that it's concave down, meaning that so for this to be relative max, what we know is that this has to be what? Positive or negative? Negative. It has to be negative for any vector u. For any u. That's what we need. So let's compute. Let's compute du. duf, that's what? That's gradient of f dotted with u. And then gradient of f is f differentiated by x, f differentiated by y. You turn it into vector, right? See, it's more convenient to just write down subscripts rather than using this type of symbol. Dotted with a comma b. And what's the dot product? You multiply component-wise. Right? So it's du of a times f of x plus b times f of y.
Then here u.
What?
That's a.
A times A times F, B times Fy. Okay? Where A and B are just some fixed constants, and Fx, Fy are still functions of x and y. Okay? So these are functions, whereas these are constants. So that's how you compute the first directional derivative. Now we have to differentiate it again using the directional derivative, which means I have to find the gradient of this again, yet again. But it's not that hard. It's all you have to do is just find the directional derivative means just find the gradient of A fx, B fy, dotted with u, and then you're trying to differentiate this and that. Well, what is a gradient? Gradient means you first differentiate this by x, and then comma, then differentiate this by y, and write it as a vector. That's all you have to do, right? So let's do that. If I differentiate this by x, tell me what I get. If I differentiate this by x, what do you get? A f x differentiated again by x. You put xx. So that's like differentiate by x, and then differentiate again by x. Okay? Plus b f y differentiated again by x. Okay? So that's the first component. That's differentiation by x. Comma. Now we have to differentiate by y. So you have a f x y differentiate by y, and this is b f y y. So I differentiated both of them by y, dotted with a comma b. Which means the first thing should be multiplied by a, so it's a squared fxx plus ab. And we just learned that when it comes to second partials, it commutes. So whether differentiating by y first and then x, or x first by y and then y, it doesn't matter. So I'm going to switch these two around. So fxy plus, and then, so that's what you get if you multiply a to both of them. Now I have to multiply b to both of them. So you have ab fxy plus b squared fyy. And now I see that these two are like terms. So you get a squared fxx plus 2ab fxy plus b squared fyy. So that was rather straightforward. I could put this as an exam question with some concrete values for a and b, right? I could put it as like 3/5, 4/5. I can give you some explicit function for f of x, y, right? Some function, and you should be able to compute this exactly like this. Okay? So that wasn't too hard. Okay? It just looks hard because I'm using a and b, and f is not explicit. But once it's explicit, you should be able to do it. Okay? Yes.
If a and b are constant, then fxx is just the second partial derivative of x.
Right.
And I mean, you can just derive that and plug it into the equation.
Yeah, you just take x and differentiate by x twice. That's all you're doing. All right, but that's not done yet. What are we trying to do here? We're trying to make sure that this is what, negative or positive? What are we trying to argue for? Negative, positive? What were we doing? Negative. We want to show that this is negative for any direction, for any constants a and b. Whether a is 1 and b is 0, or whether a is 0 and b is 1, whether a and b are both 1 over radical 2. As long as a comma b is this a comma b is a unit vector, this has to be negative for all possible values of a and b. That's why we have to ensure that this is a relative max. Okay?
Can you use numbers instead of letters?
No.
Yeah, that would be helpful.
No, I mean, I actually did this computation in the previous lecture with explicit letters, explicit numbers. I did.
On the test, we're going to be using numbers.
Yeah, so I actually did it once. So I didn't upload that video yet, but we did. Okay. And I'm just doing it in an abstract form again, but it's possible. Okay. Okay. So now let's think about how to ensure that this is always negative. To do that, what we do is we can rewrite this by taking the b squared out. A squared over b squared fxx plus 2ab over b squared fxy plus b squared over b squared fxx. So up till this part, everyone should be able to do it. This part afterwards, this is somewhat technical, so I don't expect you to be 100% following what I'm saying, but try the best you can, okay? So you should be able to follow my reasoning. Okay, so I factored out b squared, so everything is divided by b squared. And look, is b squared positive or negative?
Positive.
It's always positive, right? So that means for the entire thing to be negative, what do we need? We need this part to be negative. This has to be negative. So let's just write that only. And then here's another way to simplify. We're going to say t is equal to a over b. If I do that, then this is t squared, isn't it? And b and b cancel, so you have 2 times a over b, which is twice of t fxy. And b squared over b squared, that's 1, so it's fxx. So that's what we have. And we are trying to say that if I plug in a comma b here and here and here, this has to be negative for any value of t. That's what we are trying to say. Because a and b could be anything. T could also be anything. So whether t is negative infinity, negative 100, positive 5, or positive 1,000, this should always be negative. Yes?
What did you do with fyy?
Oh, thank you. This should be yy. I was copying it wrong. So this has to be negative always. And the way you think about this is the following. Think about it as, this is like a, 2 times fxy is like bt. So this is like, so think about this as like a times t squared, bt, and then plus c. Okay. So a is this, b is 2 times fxy, c is fyy. What kind of graph does this have? What's the shape of this graph? It's a problem, right? And we're trying to say the graph of this should be under the x-axis. When does that happen? Huh? So, huh?
When that's negative.
When all the y values are negative.
What happened to your b squared?
B squared? Oh, b squared. This is positive, so we don't care. We just have to ensure that this is negative. I need the entire thing to be negative, and I know that this is positive, so this has to be negative.
Where did t come from? What's t?
I'm writing it as t so that it's just a single value function, so that's easier to think. As I told you, this is a little more technical, so you don't have to follow everything, okay? You won't be asked to recreate this, okay? All right. So let's see what we have here. So I know that it must be like this. Agreed? Right?
Yeah.
So it relies on 2 things. First, should A be positive or negative or 0? No.
Negative.
Problem, when it's upside down, it should be negative. Okay, please think before you say it, okay? Yeah. I mean, you were thinking when you said negative, right? Yeah, for problems to be upside down. Huh?
Yeah, he's saying you're wrong.
Okay. All right. Okay, so I need this value to be negative, but we already knew that, right? Because what is A? A is f of xx, right? We already knew that. The second derivative must be negative. But that's the first condition. So the first condition that we get is fxx should be negative. That's the first condition. And then the next condition is that what can you say about the x-intercept? Does this have x-intercepts? Should it have or should it not have x-intercepts?
No, it should.
It should not have x-intercept, because if it has x-intercept, what happens?
Positive.
There are some cases where it's positive.
What if it's 0? Like if it's
If it's 0, then that's actually a thorny issue. It's yeah. We're gonna skip that discussion. Okay. All right. So let's just say we want it to not have the x-intercept at all. Okay. So that ensures that it's always below the x-axis, right? Okay. So let's do this. What is the solution to this equal to 0? The quadratic formula, right? Negative b plus minus square root of b squared minus 4ac over 2a. That's the x-intercept for this, right? Now, if this does give you two real values, is that good? No, we don't want it to be touching the x-axis at all. So what do we want? I want this to be two. What's the opposite of real value?
Imaginary.
Imaginary. I want this to be two complex numbers. How can that happen? When does that happen?
Square root of a negative.
When this is negative, right? So that's what we need. We have to say that b squared minus 4ac should be negative to ensure that everything falls under the x-axis. And what is b? b is 2 times fxy, so you have 2 times fxy squared minus 4 times, what's a? That's fxx. What's y? What's c? That's fyy. And that has to be less than 0. And that's it. Those are the two conditions. So we worked so hard to get the following fact. We worked so hard to get the following fact, which is that for relative max to happen, first we need fxx to be less than 0. And we also need, what's the square of this? This is a 4 times fxy times fxy minus 4 times fxx fyy to be less than 0. We need both. Okay. Now, this is not the form that we are going to use. Usually what we do is we first cancel out the 4. That's easier, right? And then what we do is we like to have this as positive and that as negative. So we multiply by -1 so that this turns into fxx fyy minus fxy. And then I'm going to turn one of them into fyx. And that's easier. You'll see why. Okay, so see, we learned that fxy and fyx is the same thing, right? And then I want this to be positive because if you multiply negative, the direction of the inequality changes, right? So that's the condition. And then we do one more change so that it's very easy to remember. What we do is we rewrite this as a determinant of something because it really looks like AD minus BC, right? So if I put fxx here, fyy here, so that it's like AD, and then B is fxy, and C is fyx, then this is equivalent to this determinant, and we're really saying this determinant has to be positive. And this determinant is very nice. It's easy to remember. What are we doing here? We're writing down all possible second derivatives, right? And then we're taking the determinant of that. Isn't that easy to remember, right?
Yeah.
Yeah. So this has a name. It's called the Hessian of this function. So Hessian of a function is write down all the second partials you can write, and then take the determinant. Okay. And then we need this. Okay. Now, if you think about what we did so far, this condition here has something to do with the graph never touching the x-axis. And if it never touches the x-axis, what it means is that once negative, always negative, right? So the reason that this works is for the following reason. I know that it's negative in this direction. So the second partial in x direction is negative. So it's concave down, meaning that it's like a frowning face in the x direction, right? And the second condition here says, once negative, always negative. So Hessian positive ensures that once negative, always negative. Therefore, it's a frowning face in every direction. Okay? So what can it be? Relative maximum. Okay? That's how you understand this. Okay? Okay? So let's do this. Until the second partial calculation, you should know how to do it. But this last bit, if it was hard for you, you don't have to fully understand it. So we can erase that. But you still want to have some form of intuition about that Hessian being positive. What does Hessian being positive again?
Means it's maximum.
Once negative?
Always.
No, always negative, okay? Now, then think about what would be the condition for relative minimum. First, what do we need? We need a smiley face in one direction. So what should we write? fxx
Less than 0.
less than 0 means frowning face, okay? I need smiley face, okay? So greater than 0, okay? And then what about Hessian?
That would be greater than 0, less than 0.
It's either one, right? Greater than 0 or less than 0. Which one?
Less.
Less than 0.
Bigger than 0. Okay. Why? Because this means
Once it's positive, it's always
once
positive.
positive, always positive. Thank you. Who said that? Who said that? Thank you. Yeah, that's what I mean.
Going.
All right? You need to have the correct intuition about HF. Okay?
I wouldn't.
See, this really meant that the graph doesn't touch the x-axis, so if it's under, it's always under. If it's over, it's always over. It never touches it, okay? So that's what happens. Then, think about the following case. What does it mean for h of f being negative then? It will be a saddle point. Why? Because it's like some portion are below, some portion are positive, meaning that some second partials are negative, which is like frowning face in one direction. Some second partials are positive, which is like smiley face in another direction. So it's like a saddle. Saddle. Okay? So that's why these things work. Okay?